Hello everyone, this is session 15 for the BSc third semester students of University for the mathematics course. Here I am going to cover kernel of homomorphism and fundamental theorem of homomorphism and some worked example on that. Let us recall the previous session, that was 14. What was homomorphism, isomorphism, what was the condition for homomorphism. A mapping f from G dot into G star is said to be homomorphism if for all A B belongs to B, f of A dot B must be equal to f of A star, f of B. And what was isomorphism? A mapping f from G to G is said to be isomorphism if f is homomorphism, first condition. Second was f is 1 1, third is f is on 2. Next we had properties of homomorphism. There were four properties that we have proved in the last session. Now we have kernel of homomorphism. Let us understand what is the definition of kernel of homomorphism. If f is a mapping from G to G bar, which is again a homomorphism, then the set of all those elements of G which are mapped into E bar. E bar is nothing but the identity of G bar is called the kernel of homomorphism of F. And how do we denote that? KER, that's curl of F, that's K is equal to G belongs to capital G, such that F of G must be equal to E bar. The elements of G must have the image as only E bar. That is your kernel of homomorphism. Next we have a theorem on that. That is theorem 41. The kernel K of the homomorphism F from G to G bar is a normal subgroup. As you know, to prove that it is a normal subgroup, we need to prove that x bar ax must be equal to e bar. So you have to arrive at the result. So let's write the definition of first kernel of homomorphism. What it says, this condition you have to take in the beginning here. Since f of is equal to e bar, where e belongs to k, where k is non-empty, so every g belongs to k is an element of g, which is k is a proper subset of g. First, we'll show that it is a subgroup of g, then we'll prove that it is a normal subgroup. Let AB belongs to K be some arbitrary. By the definition of kernel, we can write f of A must be equal to E bar and f of B must be equal to E bar. That means every element of G, let us take that as to be A and B, they have the image E bar, right? F of A is equal to E bar and f of B inverse is also E bar. F of A is equal to E and f of B inverse can be written as f of B whole inverse, which is equal to E. This we have written it by using your theorem 37, that is f of x inverse is equal to f of x whole inverse for all x belongs to G. Using that 37 theorem, we have written that f of a is equal to E and f of B whole inverse must be equal to E. To show that AB inverse belongs to K, consider f of AB whole inverse, which is equal to f of A. This is by using the definition of homomorphism. We can write f of AB inverse can be written as f of A dot f of B inverse. Next, this f of B inverse can be written as f of B whole inverse, keeping this f of A as it is. As you know, they have got the image E bar, so it is E bar dot E bar again by equation 1. We have written it here, right? Next, f of AB inverse must be equal to your E bar. So AB inverse belongs to K, for all B belongs to K by the definition of the kernel. So K is a subgroup of G. Further, to show that it is a normal subgroup, we need to assume X belongs to G and A belongs to K, such that X inverse AX must also belongs to K. Consider f of x inverse AX, which is equal to, again by using the property of definition of homomorphism, this is fx inverse f of A f of x. F of A is nothing but E bar, keeping this f of x as it is. F of x inverse can be written as f of x whole inverse. A belongs to K by the definition of again kernel. So it is f of x whole inverse dot f of x, that is f of x inverse AX must be equal to your E bar. By the definition of K, x inverse AX must also belongs to K for all x belongs to G, for all A belongs to K, hence K is a normal subgroup of G. Next we have theorem 42. If F is a mapping from G to G bar is a homomorphism and K is kernel of F, then F is 1 1 if and only if K is equal to E. What is given here? If F is a mapping from G to G bar, it is a homomorphism and kernel of F, then F is 1 1 if and only 1 it is going to be 1 1. If and only if K must be equal to your identity element, right? E is the identity element of G here. So now if and only if is there means we have to prove the converse part also. First we'll assume this part and we'll prove k is equal to e, and we'll take in the converse part we'll take k is equal to e and we'll prove that it is a kernel of f. Let us suppose that f is 1 1. Then for all x1 x2 belongs to g, f of x1 is equal to f of x2 where x1 is equal to x2. Call this as 1 now. For all a belongs to k, we have f of a is equal to e bar by the definition of kernel of homomorphism, e bar being the identity of your g bar. So f of a is equal to f of e. So f of e is equal to e bar by the definition of kernel of f of a. The image of e under f is e bar here. A is equal to e by equation again 1. Every element of k is e, that is k is equal to e. So we have supposed that it is 1 1 and we have arrived at this result. Now we'll suppose this k is equal to e and we'll arrive at they have got the image here. Conversely, suppose that k is equal to e, let us call this as 2. To show that f is 1 1, we need to show that every element a must have an image under f as suppose b. So let us take f of a is equal to f of b. A is equal to b for all a b belongs to g. Consider f of a is equal to f of b, which implies f of a, f of b whole inverse, taking f of b whole inverse or post multiplying f of b whole inverse on both the sides. So f of a into f of b whole inverse can be written as this f of b inverse by using the definition of homomorphism and using the theorem 37. So this is f of b inverse is nothing but your e bar. So f of ab whole inverse is equal to your e bar because f is a homomorphism. So AB inverse belongs to K by the definition of kernel. So AB inverse is equal to E. So AB just multiplying B, post multiplying B on both the sides again. So AB inverse into B is equal to E into B because B inverse into B is nothing but the identity element. So A into E is nothing but again A is equal to B here. So F of A is equal to F of B, hence F of F is 1 1. If the image is same there, then every element of G must have an image in um, G bar. So that is 1 1. Answer is 1 1. Next we have a corollary on that. And on to homomorphism, f from G to G is an isomorphism if and only if kernel of f, that is k, is equal to E. Now we'll prove that given that f is a homomorphism and on to show that f is an isomorphism, it is enough if we established f is 1 1. By theorem again 42, we have kernel of f, that is k is equal to e, f is 1 1. So k is equal to e given f is an isomorphism, that is onto homomorphism is isomorphism. So k is equal to e. Next we have theorem 43. Every quotient group G by H is a homomorphic image of G. Also the kernel of homomorphism is H. Here G is, let's prove that. Here G is a group, H is the normal subgroup of G. The quotient group G by H, this is by the definition of quotient group or factor group. HA for all events belongs to G. Define a mapping F is from G to G bar H, or G divides H by f of A is equal to HA for all it belongs to G. Call this as 1. To show that f is a homomorphism, we need to prove that f of AB is equal to f of A dot f of B for all AB belongs to G. So consider f of AB is equal to h of AB. This h of AB can be written as h of A into h of B by using the product of two cosets, right? Cosets here. For all AB belongs to G, f of A comma B is equal to A dot B is equal to f of A dot f of B by equation 1 again, hence f is a homomorphism. Since every element HA of G by H appears as an image of some element A belongs to G, so G by H is equal to f of G. That is nothing but image set here, homomorphic image of G here. So G by H is the homomorphic image of G. Now kernel of f, K is equal to, again by using the definition of kernel of homomorphism, let's call that as 2 now. To show that K is equal to H, we need to establish that K is a proper subset of H and H is a proper subset of K. To show that K is a proper subset of H, take A belongs to K arbitrary if f of A is equal to H by again definition of kernel of H is equal to H here, A belongs to H again by theorem 20. For all A belongs to K, A is belonging to H. So K is a proper subset of H here, that is for equation 3. To prove that H is a proper subset of K, let us take in a similar way. H belongs to capital H arbitrary. H into H is equal to H again by theorem 20. So f of H is equal to H into H by definition of 1 again. So similarly we can prove H is a proper subset of K. So from equation 4 and 5, and using equation 3 and 4 we can write k is equal to h. No, from equation 3 and 4 we can write this one, k is equal to h. So kernel of a homomorphism f from G to G bar h is h. Next we have very important, that is fundamental theorem of homomorphism, that is theorem 44. If f is a mapping from G to G is a homomorphism with kernel k, then f of G is isomorphic to f of G. The range set f of G is isomorphic to the quotient group G bar h, G bar k. By data, if f is a mapping from G to G is a homomorphism, the range of f, that is f of G is a subgroup of G, range of f, that is f of G is a subgroup of G such that f of G is a group. Define a new mapping, that is phi from G bar k to f of G, since k is a kernel and it is normal, so phi of k is equal to f of a for all k belongs to G by k, that is a belongs to G. Call this as 1 now. To show that phi is an isomorphism, we need to prove that it is homomorphism. It is 1 1 and it is onto. So we need to prove these three conditions. So to prove that it is homomorphism, let us take some ka and kb belongs to G bar k. Consider phi of ka dot kb. So by using the definition, this can be written as phi of kab by the definition of product of two cosets here. So this is nothing but what f of ab by the definition of phi and 1. So using this equation 1, this is f of ab. So f of ab can be written as f of a to f of b by using the definition of homomorphism. That is phi of k dot kb must be equal to phi of k dot phi of kb. That is from equation 1. So it is phi is a homomorphism. That is the first condition now. The second one is 1 1 here. To prove that phi is 1 1, let us take kb belongs to G by k. Consider phi of k is equal to phi of kb. So f of a is equal to f of b by equation 1. So post multiplying again by f of b whole inverse here. Then just simplifying this right side, this is nothing but e bar, keeping this left side as it is. And using the 37th theorem here, this is f of b inverse. So f of ab inverse, these steps are same as in the previous theorem. So ab inverse, it will be just post multiplying by b on this. So k is a proper subset of kb. Similarly, we can prove that kb is a proper subset of k. So k is equal to kb. So phi of k is equal to phi of kb, or else k is equal to kb, or else we can say that phi is 1 1 here. Now to prove that it is onto, since f of g is a range set, onto means the range set must have the images must have a pre-image here. So since f of g is a range, each of its element must appear as an image of some element of g under f here. For all b belongs to f of g, there exists some a belongs to g such that b is equal to f of a. Further, we know that for each a belongs to g, there exists k in G bar k. Thus, for all b belongs to f of g, there exists some k a belongs to G bar k, such that phi of k is equal to f of a, which is equal to b. That is, each element of f of g appears as an image of some element of G bar k under f here. That f is, which means phi is onto here. Since phi is a mapping from G bar k to f of g is an isomorphism. So G bar k is isomorphic to f of g. So that's the proof now. So we have proved the three conditions there. Next we have theorem 45. It is a similar result. If f is a mapping from G to G is an isomorphism of a group G onto G and A is any element of G, then the order of f of A equals to the order of A. Next we have theorem 46, that is f is a mapping from G to G bar is an isomorphism and G is abelian, then G bar is also abelian, we have to prove. Now to show that G bar is abelian, we need to establish that for all a bar, b bar belongs to g bar, a bar dot b bar must be equal to b bar dot a bar. That is the commutative law we have to prove. Since f is onto, for all a bar, b bar belongs to g bar, there exists some elements a, b which belongs to g such that f of a is equal to a bar and f of b is equal to b bar. Consider that product, that is a bar dot b bar, which is equal to f of a, f of b. By using the definition of homomorphism, this can be written as f of ab. Again by using ab, a dot b can be written as b dot a by using the definition of abelian or using the commutative law here. Next again by using the homomorphism, f of b dot f of a. So a bar dot b bar is equal to, now it is b bar dot a bar. For all a bar, b bar belongs to g bar, hence g bar is abelian. Next we have a similar case, that is 47. So same steps need to be proved in this case also. That is homomorphism 1 and on to for this case. We have some work examples. Show that the mapping f from r plus 2 r plus dot defined by f of x is equal to e raised to x for all x belongs to r is a homomorphism, and hence find its kernel. So they have given the definition, they have defined f of x to be e raised to x here. For all, let's take the solution now. For all x y belongs to r, consider f of x plus y is equal to e raised to x plus y by the definition of which is given here. By using the properties of exponent, we can write this is e raised to x dot e raised to y, which is equal to f of x dot f of y. F is a homomorphism because multiplication is a binary operation in R plus. To find the kernel, we know that the identity of R plus dot is 1. So e raised to 0 is 1 here, which is equal to f of 0. So kernel of f is equal to 0. Next we have the second example. Show that the function f is from R plus to C star dot defined by f of x is equal to cos x plus I sin x for all x belongs to R, where C star is equal to C minus 0 is a homomorphism and hence find its kernel. So they have defined f of x to be cos x plus I sin x. So let us take for all x y belongs to R, consider the same definition. Now using the definition of cos A plus B, the formula you have to use it here now. That is cos A cos B minus sin A sin B plus sin A cos B plus cos A sin B. Just using the the formula for cos A plus B and sin A plus B, that is cos A cos B minus sin A sin B. And for sin X plus sin A plus B, it is sin A cos B plus cos A sin B. So just take cos Y common from these two terms. So taking cos y common, what remains? Cos x plus I sin x, and here we can take I sin y common here. So what remains? Cos x plus I sin x here. I square is minus 1. So cos x plus I sin x, cos y plus I sin y, which is equal to f of x into f of y by the definition of f. The multiplication is again a binary operation in C star dot. So f is a homomorphism. To find the kernel, we know that the identity C star dot 1 can be written as 1 plus I into 0. So cos 2n pi plus I sin 2n pi. So cos 2 pi is always 0 for any value of n here now. Sin 2 pi is 0 here. So 1 is equal to f of 2n pi by the definition of f. So kernel of f will be, the images will be what now? 2n pi, where n is running from 0, 1 to 3. Now we have got the multiple choice questions. If f is a mapping from G to G is an isomorphism of a group G onto G and A is any element of G, then the order of f of A equals the order of A. That's the answer now. Next we have the second question. If f is a mapping from G to G bar is an isomorphism and G is abelian, then G bar is also abelian. Just now we have proved that result now. Next, third one, if f is a mapping from z plus to, again z plus, defined by f of x equal to 2x for all x belongs to z, is a homomorphism, then its kernel is, they should have the element as 0, the identity element. So the answer is 0 here. Next, we have the fourth question. To show that a function f is from R to R, defined by f of x is equal to x bar, the greatest integer less than or equal to x is not a homomorphism because it won't satisfy the three conditions, so it is not a homomorphism. Next, fifth one, if f of f is a mapping from R plus to R plus defined by f of x is equal to 3x plus 1 for all x belongs to R is a homomorphism. So these are the references. Thank you for watching.